There are moments when human ambition transcends the boundaries of what seems possible, when we launch not just metal and circuits into the void, but our own curiosity made manifest. Tonight, we follow one such manifestation as it drifts through the darkness between stars, carrying with it the echo of a civilization that once looked up and wondered what lay beyond. Take a deep breath, let your shoulders settle. Forget about tomorrow's meetings, about the dishes in the sink, about the endless scroll of notifications waiting on your phone. Forget about time itself. For the next few hours, we'll be traveling at 35,000 miles per hour through interstellar space, where minutes and years blend into the same infinite rhythm, where one small spacecraft continues its journey into territory no human has ever seen, armed with instruments that still, after nearly half a century, whisper secrets back to Earth. This is the story of Voyager 1, told in 100 facts that will carry you gently into sleep while expanding your mind toward the edges of everything we know. The year was 1977, and humanity stood on the threshold of something unprecedented. While most of us went about our daily routines, a small team of engineers and scientists prepared to launch what would become the most distant human-made object in existence. They couldn't have known then that their creation would still be sending data back to Earth 48 years later, or that it would fundamentally change our understanding of our place in the cosmos. But first, let us simply observe. Let us follow this remarkable machine as it moves through space that is darker and emptier than anything our planet-bound minds can truly comprehend, carrying with it not just sophisticated instruments, but a piece of Earth itself. On September 5th, 1977, at precisely 12:56 Universal Time, a Titan IIIe rocket lifted off from Launch Complex 41 at Cape Canaveral, carrying with it humanity's ambassador to the stars. The mission was initially planned to last 5 years. The spacecraft weighed 1,592 pounds, roughly the same as a small car, yet it was destined to travel farther than any human creation had ever traveled before. The launch almost didn't happen at all. Technical difficulties plagued the mission from the start, and Voyager 1 actually launched 16 days after its twin, Voyager 2, despite being designated with the lower number. This seemingly backward naming convention occurred because Voyager 1 was designed to take a faster trajectory that would allow it to reach Jupiter and Saturn before its sister spacecraft. Sometimes the obvious explanation is not the correct one, and sometimes being second out of the gate means finishing first in the race. The timing of the launch was not arbitrary. The engineers had recognized a rare celestial alignment that occurs only once every 176 years, when the 4 outer planets arrange themselves in such a way that a spacecraft could visit them all using gravitational assistance from each to reach the next. This phenomenon, dubbed the Grand Tour, would not occur again until 2153. In other words, if humanity had missed this window, none of us alive today would have lived to see another chance. Yet Voyager 1 was never intended to visit all 4 outer planets. Budget constraints forced NASA to limit the mission to Jupiter and Saturn only. The Grand Tour would be left to imagination and future generations, or so they thought. As is often the case with remarkable machines built by remarkable people, Voyager 1 had other plans. The spacecraft itself is a marvel of 1970s engineering, built at a time when pocket calculators were still relatively new and personal computers existed only in the dreams of visionaries. Its main computer has less processing power than a modern digital watch, yet it has been operating flawlessly in the hostile environment of space for nearly half a century. The computer's memory capacity is 69.63 kilobytes. To put that in perspective, this single fact about Voyager 1's computer contains more information than the spacecraft's entire memory can hold. This computer runs on something called the Command Computer Subsystem, which operates on a 16-bit architecture running at 4.77 megahertz. For comparison, a typical smartphone processor runs at speeds measured in gigahertz, making it literally thousands of times faster. Yet Voyager 1's ancient processor continues to make split-second decisions about thruster firings, instrument operations, and data transmission across distances so vast that radio signals take more than 22 hours to travel from the spacecraft to Earth. The power source for this remarkable journey comes from something called radioisotope thermoelectric generators, or RTGs. 3 of these nuclear batteries are mounted on a boom extending from the main body of the spacecraft, positioned to minimize radiation interference with the sensitive scientific instruments. Each RTG contains 24 pressed spheres of plutonium-238 oxide, a material so radioactive that it glows with its own internal heat. When Voyager 1 launched, these RTGs generated about 470 watts of electrical power, enough to run about 4 bright incandescent light bulbs. The power output decreases by approximately 4 watts per year as the plutonium naturally decays. By 2025, the spacecraft operates on less than 250 watts of power, forcing mission controllers to make difficult decisions about which instruments to keep operating and which to shut down to conserve energy. This gradual power decline creates a curious form of mechanical mortality. Unlike biological death, which often comes suddenly and unpredictably, Voyager 1's end will be slow and methodical. One by one, its instruments will go dark. First, the less critical systems, then the scientific instruments, and finally, the transmitter itself. Mission controllers estimate that the spacecraft will have enough power to operate at least one science instrument until around 2025, with the possibility of extending operations into the early 2030s if they are careful about power management. The spacecraft's physical structure consists of a 10-sided aluminum frame, giving it an almost industrial appearance that contrasts sharply with the sleek designs of modern spacecraft. This utilitarian appearance masks a sophisticated arrangement of 11 scientific instruments designed to study magnetic fields, particles, plasma waves, and cosmic rays, as well as to take photographs and make other observations of the planets and moons it would encounter. One of the most famous instruments aboard Voyager 1 is the Imaging Science Subsystem, which consists of 2 television cameras, a wide-angle camera for context, and a narrow-angle camera for detailed shots. These cameras, primitive by today's standards, captured some of the most iconic images in the history of space exploration. The narrow-angle camera has a resolution of just 800 by 800 pixels, far less than even the most basic modern digital camera, yet it managed to reveal details of Jupiter and Saturn that astronomers had never seen before. The cameras operate using something called a slow-scan Vidicon system, which builds up images line by line over a period of minutes rather than capturing them instantaneously as modern digital cameras do. This means that every image sent back by Voyager 1 represents not a frozen moment in time, but rather a gradual accumulation of light and shadow, each line building upon the last to create a complete picture. There is something almost meditative about this process, as if the spacecraft takes time to truly see each scene before committing it to memory. Perhaps the most intriguing cargo aboard Voyager 1 is something that was almost an afterthought to the mission planners. Mounted on the side of the spacecraft is a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. This golden record, as it came to be known, was the brainchild of Carl Sagan and his colleagues, who recognized that Voyager 1 might one day be found by an extraterrestrial civilization. The contents of the golden record read like a love letter from humanity to the cosmos. It contains 115 images, including photographs of people from around the world, mathematical definitions, diagrams of human anatomy, and pictures of Earth's landscapes and life forms. The audio portion includes greetings in 55 languages, sounds of Earth including wind, rain, thunder, birds, whales, and human activities, and 90 minutes of music from cultures around the globe. Among the musical selections are works by Bach, Mozart, and Beethoven, but also traditional songs from Mexico, Japan, India, and other cultures, as well as blues, jazz, and rock and roll. Chuck Berry's Johnny B. Good made it onto humanity's greatest hits album, ensuring that if aliens ever find Voyager 1, they will know that humans could make music that makes you want to dance, even in the face of cosmic insignificance. The golden record also contains the sound of a human heartbeat recorded from the chest of Carl Sagan's wife, Anne Druyan. During the recording sessions, Druyan was thinking about the history of Earth and humanity, about love, and about the possible recipients of this message. In a very real sense, the heartbeat on the golden record represents not just one human heart, but the collective pulse of an entire species, reaching out across space and time. Creating instructions for how to play the golden record presented a unique challenge. How do you explain a record player to a civilization that may have evolved along completely different technological paths? The cover of the record contains symbolic instructions showing how to play it, including a diagram of a hydrogen atom as a universal unit of measurement and a representation of the spacecraft's position relative to 14 pulsars, creating a kind of cosmic address that any scientifically advanced civilization could use to locate the origin of the message. The golden record is expected to remain playable for over 1 billion years, long after Earth's continents have shifted, long after our species has either evolved into something unrecognizable or disappeared entirely. In this sense, Voyager 1 carries not just scientific instruments, but a form of immortality for human culture, a message in a bottle cast into an ocean so vast that finding it would require luck on a scale we can barely comprehend. The trajectory that carries this message through space was carefully calculated to take advantage of a phenomenon known as gravitational assist, or gravity slingshot. This technique uses the gravitational field of a planet to alter the path and speed of a spacecraft, allowing it to reach destinations that would be impossible with chemical rockets alone. Voyager 1's path was designed to visit Jupiter first, using that planet's massive gravitational field to accelerate towards Saturn. The encounter with Jupiter began in January 1979 and provided humanity with its first close-up look at the solar system's largest planet. The images sent back by Voyager 1 revealed Jupiter as a dynamic, turbulent world, with atmospheric features changing constantly. The famous Great Red Spot, an Earth-sized storm that has been raging for at least 300 years, appeared as a complex system of swirling clouds and counter-rotating vortices. But Jupiter's moons proved even more surprising. Io, the innermost large moon, turned out to be the most volcanically active body in the solar system, with sulfur-spewing volcanoes creating a hellish landscape that resembled humanity's ancient conception of underworld realms. Europa, the second of Jupiter's 4 large moons, showed a smooth, ice-covered surface crisscrossed with fractures that suggested a liquid ocean beneath the ice, making it one of the most promising places to search for extraterrestrial life. The discovery of active volcanoes on Io was completely unexpected. No one had predicted that a moon so far from the sun would have enough internal heat to drive volcanic activity. The discovery revolutionized our understanding of how planetary bodies work and suggested that the conditions necessary for geological activity and possibly life might be far more common in the solar system than anyone had imagined. Ganymede, the largest moon in the solar system, revealed itself to be a complex world with both old, cratered terrain and younger, grooved regions that suggested past geological activity. Callisto, the outermost of Jupiter's large moons, showed a heavily cratered surface that appeared to have remained unchanged for billions of years, a kind of archaeological record of the early solar system. Perhaps most remarkably, Voyager 1 discovered that Jupiter has a ring system, something that had never been detected from Earth. The rings are extremely faint and composed mainly of dust particles, making them nearly invisible except when backlit by the sun. This discovery suggested that ring systems might be a common feature of large planets, rather than the unique characteristic of Saturn that astronomers had assumed. After its encounter with Jupiter, Voyager 1 continued on towards Saturn, reaching the ringed planet in November 1980. The images of Saturn sent back by the spacecraft exceeded even the most optimistic expectations. The ring system, viewed from close range, revealed itself to be far more complex than anyone had imagined, with thousands of individual ringlets separated by gaps and divisions. The most famous gap in Saturn's rings is called the Cassini division, discovered by Giovanni Cassini in 1675 using ground-based telescopes. From Earth, this gap appears as a dark line separating Saturn's rings into two distinct sections. Voyager 1's close-up images revealed that even the Cassini division contains several faint rings, and that the entire ring system is incredibly complex, with structures that reminded scientists of grooves on a phonograph record. Saturn's moon Titan proved to be one of the most intriguing discoveries of the Saturn encounter. Voyager 1 revealed that Titan has a thick atmosphere composed primarily of nitrogen, with clouds that completely obscure the moon's surface. This atmosphere is denser than Earth's, and contains organic compounds that may be similar to the chemicals that existed on Earth before life began. Titan became a high-priority target for future missions, eventually leading to the Cassini-Huygens mission that would arrive at Saturn 24 years later. The encounter with Titan also marked the end of Voyager 1's planetary mission. The gravitational assist from Saturn sent the spacecraft on a trajectory that would take it out of the plane of the solar system, making encounters with additional planets impossible. Mission planners had to choose between a close flyby of Titan and a trajectory that would allow the spacecraft to visit Uranus and Neptune. They chose Titan, leaving the outer planets to Voyager 2. This decision exemplifies the kind of impossible choices that define space exploration. Every mission operates under constraints of fuel, time, and physics that force difficult trade-offs. In choosing to study Titan in detail, Voyager 1 sacrificed the chance to become the first spacecraft to visit all 4 outer planets, but it provided crucial data about one of the most interesting moons in the solar system. After leaving Saturn, Voyager 1 began what is officially called the Voyager interstellar mission, although it would be decades before the spacecraft actually reached interstellar space. The primary goal of this extended mission was to study the outer regions of the solar system and the boundary between the sun's influence and interstellar space. The solar system, it turns out, is not a clearly defined sphere with sharp boundaries. Instead, it's more like a bubble blown by the solar wind, a stream of charged particles flowing outward from the sun at speeds of several hundred kilometers per second. This bubble, called the heliosphere, extends far beyond the orbit of Pluto, but its exact size and shape were unknown when Voyager 1 began its journey into the outer solar system. As Voyager 1 traveled farther from the sun, its instruments detected subtle changes in the space around it. The solar wind began to slow down and change direction as it encountered resistance from interstellar space. The magnetic field carried by the solar wind started to show signs of compression and distortion. These changes indicated that the spacecraft was approaching the heliopause, the boundary between the solar system and interstellar space. In December 2004, Voyager 1 crossed what scientists call the termination shock, the point where the solar wind slows from supersonic to subsonic speeds as it encounters the pressure of interstellar space. This was humanity's first direct measurement of this boundary, confirming theoretical predictions about the structure of the heliosphere. For several years after crossing the termination shock, Voyager 1 traveled through a region called the Helios Heath, where the solar wind continues to slow and change direction as it prepares to merge with the interstellar medium. This region turned out to be more complex and turbulent than scientists had expected, with the solar wind sometimes speeding up again and the magnetic field showing unexpected variations. On August 25, 2012, 35 years after its launch, Voyager 1 became the first human-made object to enter interstellar space. The moment was not marked by any dramatic event that could be observed in real time. Instead, it was detected months later by scientists studying data from the spacecraft's instruments, which showed that the density of charged particles around the spacecraft had suddenly increased by a factor of 40, while the strength of the magnetic field carried by the solar wind dropped to nearly zero. Entering interstellar space did not mean that Voyager 1 had left the solar system entirely. The spacecraft is still gravitationally bound to the sun, and will be for thousands of years. The Oort cloud, a spherical shell of comets that surrounds the solar system, extends roughly halfway to the nearest star. Voyager 1 will not reach the Oort cloud for another 300 years and will not pass through it completely for about 30,000 years. The environment of interstellar space turned out to be quite different from what scientists had expected. Rather than being empty and uniform, interstellar space contains a complex mixture of gas, dust, and magnetic fields left over from ancient stellar explosions and the ongoing processes of stellar evolution. The density of matter in interstellar space is extraordinarily low, about 1 atom per cubic centimeter, but this is still significantly higher than the density in the heliosheath. The temperature of interstellar space as measured by Voyager 1 is about -270 degrees Celsius, only a few degrees above absolute zero. Yet paradoxically, the few particles that exist in this space have very high energies, corresponding to temperatures of thousands of degrees. This apparent contradiction occurs because temperature in space is not the same as temperature on Earth. In the near vacuum of interstellar space, the few particles that exist can have high individual energies without creating what we would recognize as heat. One of the most important discoveries made by Voyager 1 in interstellar space is that the magnetic field there is stronger than scientists had predicted. This field appears to be aligned roughly with the direction of the spacecraft's motion, suggesting that it may be shaped by the motion of the solar system through the galaxy. The strength and direction of this field have important implications for how cosmic rays interact with our solar system and how the solar system itself moves through interstellar space. Voyager 1 has also detected what scientists call the interstellar hum, a faint but persistent signal that appears to be caused by oscillations in the interstellar plasma. This hum is so faint that it was not detected until 2017, 40 years after the spacecraft was launched. The discovery required sophisticated analysis techniques to separate the signal from background noise, and it provides the first direct measurement of the density and distribution of matter in the local interstellar medium. The spacecraft continues to send data back to Earth using a radio transmitter with a power output of just 23 watts, less than a typical fluorescent light bulb. This faint signal travels across more than 15 billion miles of space to reach the antennas of the Deep Space Network, NASA's system of radio telescopes located in California, Spain, and Australia. The fact that we can still communicate with Voyager 1 across such distances is a testament to both the skill of the engineers who designed the spacecraft and the sensitivity of modern radio telescopes. Communication with Voyager 1 is a lesson in patience. Radio signals, traveling at the speed of light, take more than 22 hours to reach the spacecraft from Earth. This means that any command sent to Voyager 1 will not be executed until nearly a full day after it is transmitted, and confirmation that the command was received will not arrive back on Earth until nearly 2 days after the original transmission. This communication delay makes real-time control of the spacecraft impossible. Instead, Voyager 1 must be largely autonomous, making decisions about instrument operations, data collection, and spacecraft orientation without waiting for instructions from Earth. The spacecraft's computer systems are programmed with complex decision trees that allow it to respond to various situations that might arise during its journey through interstellar space. Despite the limitations of 1970s computer technology, Voyager 1's systems have proven remarkably robust. The spacecraft has experienced various component failures over the years, but its redundant systems and clever engineering have allowed it to continue operating long past its original design lifetime. When primary systems fail, backup systems take over automatically. When backup systems fail, engineers on Earth work with the spacecraft's limited capabilities to find creative solutions. One of the most dramatic examples of this engineering creativity occurred in early 2024 when Voyager 1 suddenly stopped sending coherent data back to Earth. After months of investigation, engineers determined that a computer chip in the spacecraft's flight data subsystem had failed, corrupting the software code that packages data for transmission. Since they could not repair the physical chip from a distance of 15 billion miles, the engineers had to reprogram the spacecraft to work around the failed component. The solution involved relocating the affected software code to other parts of the spacecraft's memory and modifying it to work with the spacecraft's reduced capabilities. This reprogramming had to be done very carefully, since sending incorrect instructions to the spacecraft could potentially disable it entirely. The entire process took several months, during which Voyager 1 remained essentially silent. When the reprogramming was finally complete and the spacecraft began sending data again, the mission control team celebrated as if they had brought a loved one back from the dead. Similar engineering challenges have occurred throughout Voyager 1's extended mission. In 2017, engineers successfully reactivated a set of thrusters that had been dormant since 1980, extending the spacecraft's operational life by several years. These thrusters are used to orient the spacecraft's antenna toward Earth, a critical function that allows Voyager 1 to continue transmitting data. When the primary thrusters began to show signs of degradation due to fuel line clogs, engineers turned to the backup thrusters that had been sitting unused for nearly 4 decades. More recently, in 2025, engineers faced another thruster crisis when the backup thrusters also began to show signs of clogging. This time, they decided to attempt something that had been considered impossible, reactivating the original primary thrusters that had failed more than 20 years earlier. The thrusters had been declared inoperable in 2004 when their internal heaters failed, but engineers suspected that the failure might have been caused by a simple switch malfunction rather than permanent damage. The decision to attempt reactivating these long-dormant thrusters was not taken lightly. There was a real possibility that firing them could cause a catastrophic explosion that would destroy the spacecraft entirely. Engineers had to develop a procedure to test the thrusters without actually igniting them, using tiny pulses of fuel to determine whether the combustion chambers were still functional. When the tests succeeded, they cautiously fired the thrusters for the first time in 21 years. The thrusters responded perfectly, potentially extending Voyager 1's operational life by several more years. These ongoing engineering challenges highlight one of the most remarkable aspects of the Voyager 1 mission. It has been operated by 3 different generations of engineers and scientists. Many of the people who designed and built the spacecraft have retired or passed away, replaced by younger engineers who have learned to operate systems that were designed before they were born. This continuity of knowledge and expertise across decades represents one of NASA's greatest achievements. The current Voyager team includes engineers who have spent their entire careers working on the mission, becoming experts in systems that no longer exist anywhere else. They maintain detailed documentation about every component of the spacecraft, every procedure for operating it, and every quirk of its behavior developed over nearly half a century of operation. This institutional knowledge is irreplaceable, and NASA has made preserving it a high priority as the mission enters its final years. Managing Voyager 1's declining power supply has become one of the most challenging aspects of operating the spacecraft. Each year, the spacecraft has about 4 watts less power available than the year before, forcing mission managers to make difficult decisions about which systems to keep operating and which to shut down. The process is like a slow-motion version of triage, prioritizing the most scientifically valuable instruments while gradually sacrificing less critical systems. In recent years, mission managers have turned off several heaters that were designed to keep the spacecraft's instruments at optimal operating temperatures. This has caused some instruments to operate well below their design temperatures, but most have continued to function normally despite the cold. The spacecraft's cameras were shut down decades ago after completing their primary mission during the planetary encounters, but many of the other scientific instruments continue to operate and return valuable data. The scientific data being collected by Voyager 1 in interstellar space is unlike anything that has ever been obtained before. The spacecraft is sampling a region of space that no human probe has ever visited, measuring magnetic fields, particle densities, and cosmic ray intensities in an environment that can only be studied through direct observation. Every day of operation provides new insights into the nature of interstellar space and the boundary between our solar system and the galaxy beyond. One of the most significant discoveries made by Voyager 1 in interstellar space is that the boundary between the solar system and interstellar space is not static. Instead, it appears to be dynamic, moving back and forth as the pressure of the solar wind varies with the sun's 11-year activity cycle. This discovery has important implications for understanding how our solar system interacts with its galactic environment and how cosmic rays penetrate into the solar system. The cosmic ray data collected by Voyager 1 has also provided new insights into the origin and acceleration of these high-energy particles. Cosmic rays are atomic nuclei that have been accelerated to nearly the speed of light by unknown mechanisms, probably involving magnetic fields associated with exploding stars or other extreme astronomical phenomena. By measuring cosmic ray intensities both inside and outside the heliosphere, Voyager 1 has helped scientists understand how the solar system's magnetic field affects these energetic particles. Another important discovery involves the structure of the interstellar magnetic field. Voyager 1's measurements suggest that this field is more organized and stronger than scientists had expected, which has implications for understanding how our solar system moves through the galaxy and how the galaxy's magnetic field influences the solar system's structure. The spacecraft's plasma wave instrument has detected several instances of interstellar plasma oscillations, providing direct measurements of the density and temperature of the interstellar medium. These measurements are crucial for understanding the environment that our solar system is moving through and the processes that shape the structure of our local region of the galaxy. As Voyager 1 continues its journey through interstellar space, it is moving at a speed of about 17 kilometers per second relative to the Sun. At this speed, the spacecraft covers about 520 million kilometers per year, roughly the distance from the Sun to Jupiter. Yet even at this tremendous speed, Voyager 1 will not come close to another star for tens of thousands of years. The nearest star to our solar system is Proxima Centauri, located about 4.24 light-years away. Voyager 1 is not heading directly toward Proxima Centauri, but even if it were, it would take about 73,000 years to reach it at its current speed. Instead, Voyager 1 is heading roughly in the direction of the constellation Ophiuchus, and it will come within about 1.6 light-years of a star called AC plus 79 3888 in approximately 40,000 years. The longevity of Voyager 1's journey through interstellar space puts its mission in a completely different temporal context from typical human endeavors. The spacecraft will continue coasting through space long after all traces of our current civilization have disappeared from Earth. It will witness the evolution of stars, the formation of new planetary systems, and cosmic events that we can only imagine. In a very real sense, Voyager 1 has become humanity's most permanent creation, an artifact that will outlast not only our species, but our entire solar system. The golden record aboard Voyager 1 was designed with this longevity in mind. The record is made of gold-plated copper, materials chosen for their resistance to corrosion and their ability to preserve information over cosmic timescales. The record is protected by an aluminum cover that shields it from the micrometeorite impacts and radiation that the spacecraft encounters during its journey. According to the scientists who designed it, the golden record should remain playable for over 1 billion years. The information on the golden record represents a snapshot of Earth and human civilization as it existed in 1977. The images include photographs of human beings from various cultures, examples of Earth's geography and biological diversity, and diagrams explaining basic scientific concepts. The audio portion includes not only music and greetings, but also sounds that the record's creators thought would convey something essential about life on Earth: a crying baby, laughter, the sound of ocean waves, and the songs of whales. Carl Sagan, who who led the committee that selected the contents of the Golden Record, described it as a message of peace and hope intended for any extraterrestrial civilization that might eventually encounter Voyager 1. The record includes no images of war, violence, or human suffering, presenting instead an idealized version of human civilization. Critics have argued that this presents a misleading picture of humanity, but Sagan argued that the record should represent humanity at its best, not its worst. The mathematical and scientific information on the Golden Record is designed to be universal, understandable to any scientifically advanced civilization, regardless of their specific evolutionary history or technological development path. The record includes diagrams showing the structure of the hydrogen atom, mathematical definitions, and a map showing Earth's location in the galaxy relative to 14 pulsars. These pulsars serve as cosmic lighthouses, each with a unique signature that should allow any civilization with advanced astronomy to determine both the location and the time period when the record was created. The possibility that the Golden Record will ever be found by an extraterrestrial civilization is extraordinarily small. Space is so vast and empty that the chances of Voyager 1 being intercepted are essentially zero. Frank Drake, the astronomer who helped design the record, estimated that the probability of its being found is less than 1 in a trillion. Yet the record serves an important purpose even if it is never found. It forces us to think about how we would present ourselves to an alien intelligence and what aspects of human civilization we consider most important and worthy of preservation. The creation of the Golden Record also represents one of the first serious attempts by humanity to create a message intended for non-human intelligence. The committee that designed the record had to grapple with fundamental questions about communication, culture, and what makes us human. How do you explain music to a civilization that might not have evolved hearing? How do you convey the concept of love to beings that might reproduce in ways completely different from humans? How do you represent the diversity of human culture in a limited space? These questions have no definitive answers, but the process of attempting to answer them provided valuable insights into human nature and our place in the cosmos. The Golden Record Project required its creators to step outside their own cultural assumptions and try to see humanity from an external perspective. This exercise in cosmic empathy was perhaps as valuable as any scientific data that Voyager 1 has collected. The technical specifications of Voyager 1 reflect the engineering limitations and capabilities of the 1970s, but also demonstrate remarkable foresight on the part of the mission designers. The spacecraft was built to operate for 5 years, yet it has continued functioning for nearly 10 times its designed lifetime. This longevity is the result of conservative engineering, extensive redundancy, and high-quality components, but also of plain good luck. The spacecraft's structure is built around a 10-sided aluminum framework that houses the various electronic systems and provides mounting points for the scientific instruments and the large parabolic antenna used for communication with Earth. The entire structure is designed to be lightweight yet rigid enough to survive the stresses of launch and the thermal cycling that occurs as the spacecraft moves between sunlight and shadow. The spacecraft's orientation in space is controlled by a system of small thrusters that use hydrazine fuel. These thrusters can rotate the spacecraft around 3 axes, allowing mission controllers to point the antenna toward Earth and orient the scientific instruments toward their targets. The thrusters are designed to operate with extreme precision, capable of making adjustments measured in fractions of a degree. The electrical power system consists of 3 radioisotope thermoelectric generators that convert the heat from radioactive decay directly into electricity. This system was chosen over solar panels because Voyager 1 was designed to operate at distances from the Sun where solar panels would be ineffective. The RTGs have no moving parts and are extremely reliable, but their power output decreases gradually over time as the radioactive fuel decays. The communication system uses a 3.7-meter parabolic antenna to transmit data back to Earth using radio waves in the X-band and S-band frequencies. The antenna must be pointed very precisely toward Earth to maintain communication, requiring constant adjustments as both the spacecraft and Earth move through their orbits. The transmitted signal is extremely weak by the time it reaches Earth, requiring very sensitive receiving equipment and sophisticated signal processing techniques to extract the data from background noise. Data storage aboard Voyager 1 is provided by 2 digital tape recorders, each capable of storing about 67 megabytes of information. By modern standards, this storage capacity is tiny, but it was revolutionary for its time. The tape recorders use magnetic tape similar to that used in audio cassettes, but specially designed to operate in the harsh environment of space for decades. The scientific instruments aboard Voyager 1 were selected to study a wide variety of phenomena during the spacecraft's encounters with Jupiter and Saturn. These instruments include magnetometers to measure magnetic fields, particle detectors to study charged particles and cosmic rays, plasma wave sensors to detect oscillations in ionized gas, and radio receivers to study radio emissions from planets and their moons. The twin cameras that captured the iconic images of Jupiter and Saturn are probably the most famous instruments aboard Voyager 1. The wide-angle camera has a focal length of 200 millimeters and provides context for the narrow-angle camera, which has a focal length of 1,500 millimeters and can resolve features as small as a few kilometers on planetary surfaces. Both cameras use Vidicon tubes, television technology that was state-of-the-art in the 1970s, but seems primitive compared to modern digital cameras. The images captured by these cameras had to be transmitted back to Earth one line at a time, a process that could take hours for a single photograph. Each image was broken down into 800 horizontal lines, with each line containing 800 individual picture elements or pixels. The brightness of each pixel was encoded as a digital number and transmitted to Earth using the spacecraft's radio transmitter. On Earth, these digital numbers were used to reconstruct the original image. This process of transmitting images across interplanetary distances required careful attention to data compression and error correction. The amount of data in a single Voyager image was enormous by 1970s standards, and the weak radio signal meant that data transmission rates were very slow. Mission controllers had to balance image quality against transmission time, often choosing to send fewer, higher quality images rather than more images at lower resolution. The navigation of Voyager 1 through the solar system required extraordinarily precise calculations and constant course corrections. The spacecraft's trajectory was planned years in advance using sophisticated computer models that took into account the gravitational effects of the Sun, planets, and even the larger moons. Small errors in these calculations could cause the spacecraft to miss its targets by thousands of kilometers, so navigation accuracy was critical to mission success. Course corrections were made using the spacecraft's thrusters, which could change its velocity by a few meters per second in any direction. These corrections were planned carefully to minimize fuel consumption while ensuring that the spacecraft would arrive at its targets at the proper times and distances. The navigation team had to plan not only for the primary mission objectives at Jupiter and Saturn, but also for the extended mission that would take the spacecraft into interstellar space. The timing of Voyager 1's encounters with Jupiter and Saturn was carefully planned to provide the best scientific observations, while also setting up the trajectory for the interstellar mission. The spacecraft's flyby of Saturn was designed to provide a close encounter with Titan while also deflecting the spacecraft's path northward out of the plane of the solar system. This trajectory choice meant that Voyager 1 would not be able to visit Uranus and Neptune, but it provided the fastest route to interstellar space. The gravitational assist technique used by Voyager 1 is sometimes called a gravity slingshot, but this analogy is somewhat misleading. The spacecraft does not bounce off planets like a ball bouncing off a wall. Instead, it follows a curved trajectory through each planet's gravitational field, gaining energy from the planet's orbital motion around the Sun. This technique allows spacecraft to reach much higher speeds than would be possible with rocket propulsion alone. The physics of gravitational assist is based on the conservation of energy and momentum, As Voyager 1 approaches a planet from behind in its orbit, it falls into the planet's gravitational field and gains speed. When it leaves the planet's gravitational field on the other side, it retains this extra speed, having effectively stolen a tiny amount of orbital energy from the planet. The planet's orbit is slowed by an infinitesimal amount, but because the planet is so much more massive than the spacecraft, this effect is completely negligible. The success of gravitational assist maneuvers depends on extremely precise navigation and timing. The spacecraft must arrive at exactly the right place at exactly the right time to achieve the desired trajectory change. Small errors in navigation can result in trajectories that miss the target planet entirely or provide much less gravitational assist than planned. The navigation teams for both Voyager spacecraft achieved remarkable precision, with trajectory errors typically measured in kilometers rather than miles, the hundreds of kilometers that were considered acceptable for earlier missions. The encounter sequences at Jupiter and Saturn were among the most complex operations ever attempted in space exploration. During each encounter, Voyager 1 had to execute a precisely choreographed sequence of observations, taking thousands of images and measurements while moving past the planet at speeds of several kilometers per second. The spacecraft's computer systems had to be programmed in advance with detailed instructions for pointing the instruments and cameras, taking data, and transmitting the results back to Earth. The data collected during these encounters far exceeded the expectations of the mission planners. The discovery of active volcanoes on Io came as a complete surprise, as did the complex structure of Saturn's rings and the thick atmosphere of Titan. Each new discovery raised new questions and provided new insights into the formation and evolution of the solar system. The images of Earth taken by Voyager 1 from the outer solar system have become some of the most famous photographs in history. The most iconic of these is the pale blue dot image, taken from a distance of about 6 billion kilometers as the spacecraft looked back toward the inner solar system. In this image, Earth appears as a tiny speck of light suspended in a sunbeam, demonstrating the cosmic insignificance of our planet while simultaneously highlighting its unique importance as the only known harbor for life. Carl Sagan used this image as the basis for one of his most famous speeches, reflecting on the fragility and uniqueness of Earth as seen from the perspective of deep space. He noted that every human who has ever lived has done so on that tiny speck of light, that all of our wars, triumphs, and tragedies have occurred within the boundaries of that barely visible dot. The image serves as a powerful reminder of our common humanity and our shared responsibility for the only planet we know that can support life. The pale blue dot photograph required special effort to obtain. By the time Voyager 1 was 6 billion kilometers from Earth, its primary mission was complete, and its cameras were normally turned off to conserve power and computer resources. Sagan had to lobby NASA management for years to approve a final series of images looking back at the solar system. The images were finally taken on February 14, 1990, as part of what was called the Solar System Family Portrait, a series of images showing 6 of the solar system's planets from Voyager 1's unique vantage point. Taking the pale blue dot image was not without risks. Pointing the camera toward the inner solar system meant pointing it relatively close to the sun, which could have damaged the sensitive Vidicon tube if the pointing was not extremely precise. The image had to be carefully planned to avoid direct sunlight while still capturing Earth within the camera's field of view. The result was an image that has inspired millions of people to think about Earth's place in the cosmos. The scientific legacy of Voyager 1 extends far beyond its famous images and discoveries. The spacecraft has fundamentally changed our understanding of the outer solar system and provided the first direct measurements of interstellar space. Its discoveries have influenced the design of subsequent missions and continue to shape our understanding of planetary science and space physics. The discovery of volcanic activity on Io led to a complete revision of theories about tidal heating and geological activity on small bodies. Scientists now understand that moons in the outer solar system can remain geologically active for billions of years due to tidal forces from their parent planets, opening up the possibility that many of these moons might harbor conditions suitable for life. The complex structure of Saturn's rings revealed by Voyager 1 demonstrated that these seemingly simple features are actually dynamic systems governed by gravitational interactions with small moons and the complex physics of particle collisions. This understanding has been applied to other ring systems in the solar system and has even provided insights into the formation of planetary systems around other stars. The measurements of interstellar space made by Voyager 1 have provided the first direct evidence for theories about the structure of the heliosphere and the nature of the interstellar medium. These measurements are crucial for understanding how our solar system interacts with the galaxy and how galactic processes affect conditions within the solar system. The longevity of Voyager 1 has also provided valuable lessons about spacecraft design and mission operations. The conservative engineering approach used for the Voyager spacecraft has influenced the design of subsequent deep space missions, emphasizing reliability and redundancy over cutting-edge technology. The mission has demonstrated that well-designed spacecraft can operate far beyond their intended lifetimes if they are built with sufficient margins and flexibility. The ongoing operation of Voyager 1 requires a small but dedicated team of engineers and scientists who have become experts in maintaining and operating systems that are decades old. This team has developed innovative techniques for extending the spacecraft's operational life, including creative reprogramming to work around failed components and careful power management to maximize the remaining operational time. The communication challenges posed by Voyager 1's increasing distance from Earth have pushed the development of deep space communication techniques and technologies. The Deep Space Network has been upgraded multiple times over the mission's lifetime to maintain communication with the spacecraft, and new signal processing techniques have been developed to extract weak signals from background noise. As Voyager 1 continues its journey through interstellar space, it serves as humanity's first interstellar probe, carrying not only scientific instruments, but also a message from Earth to any civilization that might eventually find it. The spacecraft represents humanity's first step beyond the solar system, a tentative exploration of the galaxy that surrounds us. The data being returned by Voyager 1 from interstellar space is unprecedented and irreplaceable. Each day of operation provides new information about an environment that no other human probe has ever sampled. The measurements of magnetic fields, particle densities, and plasma waves in interstellar space are building a picture of our galactic neighborhood that could not be obtained in any other way. The gradual decline of Voyager 1's power systems means that the mission will eventually come to an end, probably sometime in the late 2020s or early 2030s. When the last instrument finally falls silent, it will mark the end of one of the most successful and productive missions in the history of space exploration. Yet even after it stops transmitting, Voyager 1 will continue its journey through the galaxy, carrying the golden record and its message from Earth into the far future. The legacy of Voyager 1 extends beyond its scientific discoveries to its impact on human culture and consciousness. The mission has provided a new perspective on our place in the cosmos, demonstrating both the vastness of space and the uniqueness of Earth. Its images and discoveries have inspired countless people to pursue careers in science and engineering, and its message of peaceful exploration continues to resonate with people around the world. The story of Voyager 1 is ultimately a story about human curiosity and ingenuity. It represents our species' desire to explore and understand the universe around us, even when that exploration takes us to places we may never be able to visit in person. The spacecraft embodies our finest aspirations as a species, our dedication to knowledge, our commitment to peaceful exploration, and our hope that we are not alone in the universe. As we drift toward sleep, consider this remarkable machine as it moves through the darkness between stars at 17 kilometers per second, its instruments still functioning, still observing, still learning. Consider the golden record it carries, with its sounds of Earth and its message of peace and hope, Consider the team of engineers and scientists who continue to care for it across the vast distance that separates us, maintaining a connection to humanity's most distant creation. In the silence of space, where no sound can travel, Voyager 1 continues its eternal journey, carrying with it the hopes and dreams of a species that dared to reach beyond its homeworld. It moves through a realm where the familiar rules of terrestrial existence give way to the strange physics of interstellar space, where individual particles carry the energy of lightning, but the temperature approaches absolute zero. And in that silence, in that darkness, in that cold, there is something profoundly moving about this small machine continuing its mission, sending back faint whispers of data across 15 billion miles of emptiness, reminding us that even in the face of cosmic vastness, human curiosity and ingenuity can touch the infinite. The people who built Voyager 1 worked with slide rules and early computers that filled entire rooms. They used materials and techniques that seem almost medieval compared to modern spacecraft construction, yet they created something that has outlasted most of the technology that has followed it. The spacecraft's aluminum frame was machined using techniques developed for aircraft construction. Its wiring was hand-soldered by technicians who took pride in creating connections that would last for decades in the harsh environment of space. The quality control procedures used during Voyager 1's construction were extraordinarily rigorous, even by the standards of aerospace engineering. Every component was tested multiple times under conditions more severe than anything the spacecraft would encounter during its mission. Vibration tests simulated the violent shaking of launch. Thermal vacuum tests exposed components to temperature extremes far beyond what they would experience in space. Electromagnetic compatibility tests ensured that the various systems would not interfere with each other during operation. These tests revealed numerous problems that were fixed before launch, but they could not anticipate every challenge that the spacecraft would face during its decades-long mission. The engineers built flexibility into the design, creating multiple backup systems and programming the computers with decision-making capabilities that would allow the spacecraft to respond to unforeseen circumstances. The software that runs Voyager 1's computers was written in assembly language, the most basic form of computer programming that directly controls the spacecraft's processors. Every instruction had to be carefully crafted and tested, since there was no operating system to handle routine tasks automatically. The programmers had to account for every byte of memory and every cycle of processor time, creating code that was both efficient and reliable. This software has been modified hundreds of times during the mission, with new instructions uploaded from Earth to change the spacecraft's behavior or work around failed components. Each modification requires careful analysis to ensure that it will not interfere with other systems or create new problems. The fact that software written in the 1970s continues to operate reliably after nearly 5 decades of continuous operation is a testament to the skill of the original programmers. The Deep Space Network that maintains communication with Voyager 1 consists of 3 complexes of radio antennas located approximately 120 degrees apart around the Earth. This spacing ensures that at least one complex can always see the spacecraft as the Earth rotates. The antennas are among the most sensitive radio telescopes in the world, capable of detecting signals so weak that they would be overwhelmed by the radiation from a cell phone held on the Moon. The largest antennas in the Deep Space Network are 70 meters in diameter, roughly the size of a football field. These massive dishes can be pointed with extraordinary precision, maintaining communication with spacecraft that appear to move across the sky as both the Earth and the spacecraft move through their orbits. The pointing accuracy required is comparable to hitting a dime with a laser pointer from a distance of several miles. The radio signals from Voyager 1 arrive at Earth with a power of about 10 to the minus 16 watts, 1/10 quadrillionth of a watt. To put this in perspective, it would take more energy to lift a feather 1 centimeter than Voyager 1's signal delivers to Earth in an entire year. Yet sophisticated amplifiers and signal processing techniques can extract meaningful data from these incredibly weak signals. The data transmission rate from Voyager 1 has decreased over the years as the spacecraft has moved farther from Earth and its transmitter power has declined. Currently, the spacecraft can transmit data at a rate of only 160 bits per second, slower than the dial-up internet connections that were common in the 1990s. At this rate, it would take more than 3 days to transmit a single photograph from a modern digital camera. Despite these limitations, Voyager 1 continues to return scientifically valuable data from its instruments. The spacecraft's cosmic ray detector measures the intensity and energy distribution of high-energy particles in interstellar space. These measurements provide insights into the mechanisms that accelerate cosmic rays and the magnetic field structure of our local region of the galaxy. The plasma wave instrument aboard Voyager 1 has detected several different types of oscillations in the interstellar plasma, each providing information about different aspects of the interstellar environment. Some of these oscillations are caused by the interaction between the solar wind and the interstellar medium, while others appear to be generated by processes within the interstellar medium itself. One of the most intriguing discoveries made by Voyager 1 involves the magnetic field structure in interstellar space. The field appears to be more organized than scientists had expected, suggesting that it may be shaped by large-scale galactic processes, such as stellar winds from nearby stars or the rotation of the galaxy itself. Understanding this magnetic field structure is crucial for predicting how cosmic rays propagate through the galaxy and how they might affect life on planets throughout the galaxy. The temperature measurements made by Voyager 1 in interstellar space reveal a complex environment where different components of the interstellar medium exist at very different temperatures. The electrons in the plasma have temperatures of thousands of degrees, while the overall kinetic temperature of the medium is only a few degrees above absolute zero. This temperature structure provides clues about the energy sources that heat the interstellar medium and the processes that govern its evolution. The density of the interstellar medium as measured by Voyager 1 is remarkably uniform, suggesting that the spacecraft is traveling through a relatively smooth region of space. However, subtle variations in density provide evidence for waves and turbulence in the interstellar plasma, probably generated by the complex interactions between stellar winds from different stars and the remnants of ancient supernovae. These measurements of the interstellar medium are particularly valuable because they provide ground truth for astronomical observations made from Earth. Astronomers can observe the interstellar medium throughout the galaxy using telescopes, but these observations must be interpreted using models that make assumptions about the properties of interstellar space. Voyager 1's direct measurements provide a way to test and calibrate these models. The scientific instruments aboard Voyager 1 were designed in the 1960s and early 1970s, using technology that was state-of-the-art for that era, but seems primitive by modern standards. The cosmic ray detector uses solid-state detectors similar to those used in early semiconductor devices. The magnetometer uses flux gate sensors, a technology developed during World War II for detecting submarines. Yet these instruments continue to operate reliably and provide data that modern instruments would be hard-pressed to improve upon. The longevity of these instruments is partly due to the conservative design philosophy used throughout the Voyager program. Rather than pushing the limits of technology, the engineers chose proven techniques and built in large safety margins. Components were selected for reliability rather than performance, and extensive redundancy was incorporated into critical systems. This approach has paid dividends throughout the extended mission. When primary systems have failed, backup systems have taken over seamlessly. When backup systems have failed, engineers have found creative ways to use remaining systems to accomplish mission objectives. The spacecraft has proven to be remarkably adaptable, continuing to operate under conditions that were never anticipated by its designers. The thermal control system that keeps Voyager 1's instruments at operating temperature has been one of the most challenging aspects of the extended mission. The spacecraft was designed to operate in the relatively warm environment near Jupiter and Saturn, where solar heating and planetary radiation provide significant thermal input. In the cold depths of interstellar space, maintaining proper temperatures has required creative power management and selective heating. Many of Voyager 1's instruments are now operating well below their design temperatures, yet most continue to function normally. This is partly due to the robust design of the instruments, and partly due to the benign environment of interstellar space, where there are no corrosive atmospheres or extreme temperature cycling to cause component degradation. The power management challenges faced by the Voyager team have required increasingly creative solutions as the spacecraft's power output has declined. Engineers have developed techniques for operating instruments intermittently, turning them on only when data is being collected and shutting them down during transmission periods to conserve power. They have also found ways to extract useful data from instruments operating at reduced power levels. The fuel management for Voyager 1's thrusters has become increasingly critical as the mission has progressed. The hydrazine fuel used by the thrusters slowly decomposes over time, creating byproducts that can clog fuel lines and degrade thruster performance. Engineers have developed procedures for cleaning fuel lines and optimizing thruster performance to extend the operational lifetime of the attitude control system. The thruster system aboard Voyager 1 consists of 16 small rockets arranged in 4 groups around the spacecraft. Each thruster produces only about 0.9 newtons of force, roughly equivalent to the weight of a small apple, yet this tiny amount of thrust is sufficient to orient the massive spacecraft and maintain its antenna pointing toward Earth. The precision required for these pointing maneuvers is extraordinary, with errors measured in fractions of a degree. The guidance and navigation system that controls these thrusters uses a combination of star trackers, sun sensors, and inertial measurement units to determine the spacecraft's orientation in space. The star tracker locks onto a bright star and uses it as a reference point, while the inertial measurement units detect any rotation of the spacecraft. The computer system combines information from these sensors to determine the precise thruster firings needed to maintain proper orientation. This guidance system has operated continuously for nearly 5 decades, making tiny corrections to the spacecraft's orientation thousands of times per day. The accumulated accuracy of these corrections has been remarkable, with pointing errors typically remaining well within acceptable limits, despite the gradual degradation of sensors and the increasing distance from Earth. The communication protocol used between Voyager 1 and Earth has evolved significantly over the course of the mission. Originally designed for relatively high data rates during the planetary encounters, the protocol has been modified to work efficiently at the much lower data rates available during the interstellar mission. These modifications have involved changes to both the spacecraft software and the ground-based receiving equipment. Error correction techniques have become increasingly important as Voyager 1's signal has weakened. The original communication system included basic error detection and correction capabilities, but these have been supplemented with more sophisticated algorithms implemented in the ground-based receivers. These techniques can recover useful data even when the received signal is almost completely overwhelmed by noise. The timing of communication sessions with Voyager 1 must be carefully planned to account for the motion of both the spacecraft and the Earth. As the Earth rotates, different antennas in the deep space network come into view of the spacecraft, requiring seamless handoffs to maintain continuous communication. These handoffs must be timed precisely to avoid losing data during transmission. The daily routine of operating Voyager 1 involves a complex choreography of antenna pointing, data transmission, and command sequences. Each day, mission controllers upload a new set of instructions to the spacecraft, telling it which instruments to operate, when to transmit data, and how to orient itself. The spacecraft executes these instructions autonomously, since the long communication delay makes real-time control impossible. The data analysis process for Voyager 1 involves scientists from around the world who specialize in different aspects of space physics and planetary science. Raw data from the spacecraft must be processed to remove instrumental effects and calibrated using laboratory measurements and theoretical models. This process can take months or even years for complex data sets. The scientific publications resulting from Voyager 1's observations number in the thousands, covering topics from the atmospheric dynamics of Jupiter to the structure of the interstellar medium. Each new discovery builds upon previous knowledge and often leads to new questions that drive future research. The mission has been one of the most scientifically productive in the history of space exploration. The engineering innovations developed for Voyager 1 have influenced the design of subsequent spacecraft missions. Techniques for long-duration space operations, deep space communication, and autonomous spacecraft control were pioneered by the Voyager program and have been applied to missions throughout the solar system. The conservative design philosophy that has made Voyager so successful continues to influence spacecraft design today. The cultural impact of Voyager 1 extends far beyond the scientific community. The spacecraft's images of the outer planets changed public perception of the solar system, revealing worlds of extraordinary beauty and complexity that captured the imagination of people around the world. The pale blue dot image has become an icon of the environmental movement, reminding us of Earth's fragility and uniqueness. The golden record has become, perhaps, the most famous artifact of human culture ever created. Its contents have been analyzed by anthropologists, musicologists, and philosophers as a window into how humans of the 1970s saw themselves and their place in the universe. The record represents an idealized version of humanity, emphasizing our achievements in science, art, and culture while omitting the darker aspects of human nature. The selection process for the Golden Record's contents was both collaborative and contentious. The committee responsible for the record included scientists, artists, and cultural experts from around the world, but they had to work within strict constraints of time, space, and technology. Every decision about what to include meant leaving something else out, and the committee struggled with questions about how to represent the diversity of human culture fairly. The music on the Golden Record ranges from Bach to Chuck Berry, from traditional folk songs to modern classical compositions. The selection was intended to demonstrate the universality of human musical expression, while also showcasing the diversity of cultural traditions around the world. Some critics have argued that the selection reflects the biases of the predominantly Western committee, but others point out that the record was never intended to be a comprehensive survey of human music. The images on the Golden Record include both scientific diagrams and artistic photographs intended to convey the beauty and diversity of life on Earth. The scientific images include mathematical definitions, anatomical diagrams, and illustrations of DNA structure, while the artistic images show landscapes, animals, and people from around the world. The challenge was to select images that would be meaningful to an alien intelligence while also representing the full spectrum of Earth's environments and life forms. The spoken greetings on the Golden Record were recorded in 55 languages, from major world languages like English and Mandarin to lesser-known languages representing indigenous cultures. Each greeting was brief, typically lasting only a few seconds, but collectively they demonstrate the linguistic diversity of human civilization. The greetings were recorded by native speakers, many of whom were students or faculty at Cornell University, where Carl Sagan worked. The sounds of Earth included on the Golden Record were chosen to represent the acoustic environment of our planet. These range from natural sounds like wind, rain, and ocean waves to biological sounds like bird songs, whale calls, and human laughter. The selection also includes human-made sounds like footsteps, heartbeats, and the sound of a kiss, intended to convey the more intimate aspects of human experience. One of the most poignant sounds on the Golden Record is the cry of a baby, recorded specifically for the project. This sound, universal to human experience, regardless of culture or language, was intended to convey something essential about human nature to any alien intelligence that might eventually find the record. The baby's cry represents both vulnerability and potential, capturing the essence of what it means to be human. The technical challenge of creating a playable record that would survive in space for potentially billions of years required innovative materials and manufacturing techniques. The record itself is made of gold-plated copper, chosen for its resistance to corrosion and its ability to maintain surface quality over cosmic timescales. The protective cover is made of aluminum and includes instructions for playing the record etched into its surface. The instructions for playing the golden record are themselves a masterpiece of cross-cultural communication. They use pictographs and mathematical symbols to explain how to extract audio and images from the record, assuming only that any technological civilization would understand basic physics and mathematics. The instructions include a diagram of a hydrogen atom as a universal unit of time and distance, and a map showing Earth's location relative to nearby pulsars. The decay of the radioactive elements in Voyager 1's power source follows a precise mathematical curve that allows engineers to predict exactly how much power will be available at any future time. This predictability is both a blessing and a curse for mission planners, as it provides certainty about the spacecraft's remaining lifetime while also imposing hard limits on future operations. Current projections suggest that Voyager 1 will have enough power to operate at least one scientific instrument until sometime between 2025 and 2030, depending on which instruments are kept running and how efficiently power is managed. After that point, the spacecraft will continue to coast through interstellar space, but it will no longer be able to communicate with Earth or collect scientific data. The final phase of Voyager 1's operational life will require difficult decisions about which instruments to keep running and which to shut down. Mission managers must balance scientific priorities against power constraints, choosing to maintain the instruments that are most likely to make important discoveries during the spacecraft's remaining operational time. The plasma wave instrument, which has provided some of the most important discoveries about interstellar space, is likely to be among the last instruments operating. This instrument requires relatively little power and provides unique information about the density and temperature of the interstellar medium that cannot be obtained in any other way. The magnetometer, which measures the strength and direction of magnetic fields in interstellar space, is another high-priority instrument for the final phase of the mission. The magnetic field measurements are crucial for understanding how the solar system interacts with the interstellar medium and how galactic magnetic fields influence the structure of interstellar space. When Voyager 1 finally falls silent, it will mark the end of humanity's first interstellar mission, but the beginning of an even longer journey. The spacecraft will continue to coast through the galaxy for millions of years, gradually moving away from the Sun and eventually passing close to other star systems. In about 40,000 years, it will come within 1.6 light-years of the star AC plus 793888 in the constellation Camelopardalis. The probability that Voyager 1 will ever be found by an extraterrestrial civilization is vanishingly small, but not zero. The spacecraft is built to last, and the golden record is designed to remain playable for over 1 billion years. If it is ever found, it will provide a snapshot of human civilization from the late 20th century, a time capsule from a species that dared to reach beyond its home planet. The legacy of Voyager 1 extends beyond its scientific discoveries to its impact on human consciousness and culture. The mission has provided a new perspective on our place in the universe, demonstrating both the vastness of space and the uniqueness of Earth. Its discoveries have influenced science fiction, art, and philosophy, inspiring new ways of thinking about humanity's relationship with the cosmos. The photographs taken by Voyager, one of the outer planets, have become part of our collective visual vocabulary, influencing how we imagine alien worlds and the possibilities for life beyond Earth. The complex moons of Jupiter and Saturn revealed by the mission have become targets for future exploration, with several missions currently planned or under development to study these intriguing worlds in greater detail. The technological challenges overcome during the Voyager 1 mission have driven advances in spacecraft design, deep space communication, and autonomous operation that benefits all subsequent space missions. The techniques developed for navigating through the outer solar system and maintaining communication across interplanetary distances are now standard practices in space exploration. The international cooperation that has characterized the Voyager program has served as a model for subsequent space missions. Scientists from around the world have collaborated on data analysis and interpretation, sharing knowledge and expertise across national boundaries. This spirit of international cooperation in the pursuit of scientific knowledge represents humanity at its best. The educational impact of Voyager 1 has been immeasurable, inspiring generations of students to pursue careers in science, technology, engineering, and mathematics. The mission has provided compelling examples of how theoretical knowledge can be applied to solve practical problems, demonstrating the value of basic research and scientific education. The philosophical implications of Voyager 1's journey continue to resonate with thinkers and writers around the world. The mission has provided concrete evidence of humanity's ability to transcend the limitations of our home planet, while also highlighting the precious and fragile nature of the only world we know that can support life. As Voyager 1 continues its eternal journey through the darkness between stars, it carries with it not just scientific instruments and cultural artifacts, but the hopes and dreams of an entire species. It represents our desire to explore and understand the universe around us, our commitment to peaceful exploration, and our faith that knowledge and curiosity can triumph over ignorance and fear. In the vast emptiness of interstellar space, where the nearest star is trillions of miles away and the space between atoms is measured in meters rather than nanometers, this small machine continues its patient work. Its instruments sample an environment that no human will ever visit. Its radio transmitter whispers data across distances that dwarf human comprehension, and its golden record carries a message of peace and goodwill into the far future. The story of Voyager 1 is ultimately a story about the power of human imagination and ingenuity. It began with dreamers who looked up at the night sky and wondered what lay beyond, continued with engineers and scientists who turned those dreams into reality, and persists with the dedicated team that continues to operate this remarkable machine across the vast gulf of space and time. As you settle into sleep tonight, imagine this small ambassador of humanity moving silently through the cosmic night, its instruments still functioning, its mission still unfolding, its message still traveling toward an unknown future. In the silence of space, where no sound can travel, Voyager 1 continues to speak for all of us, carrying our voice into the darkness and demonstrating that even the smallest light can illuminate the infinite. The gentle hum of its electronics, the steady pulse of its transmitter, the patient sweep of its instruments across the alien landscape of interstellar space, all of these continue in a rhythm as steady and eternal as a heartbeat, as constant as the turning of the earth, as enduring as human curiosity itself. And in that steady rhythm, in that eternal persistence, in that unwavering dedication to discovery and exploration, there is something deeply peaceful, something that speaks to the best parts of human nature, something that reminds us that no matter how vast and dark the universe might seem, we are not alone, as long as we continue to reach out with curiosity and wonder toward the infinite mystery that surrounds us all. The world that built Voyager 1 was profoundly different from the world we inhabit today. In 1977, personal computers were still the stuff of science fiction for most people. The internet existed only as a theoretical concept in a few research laboratories. Cell phones were bulky devices used primarily by business executives and emergency workers. Most people received their news from newspapers, radio, and 3 television networks. The idea that ordinary citizens would one day carry devices more powerful than the computers that guided Voyager to Jupiter seemed absurdly optimistic. Yet the engineers and scientists who designed Voyager 1 possessed something that transcended the technological limitations of their era, an unshakable faith in human ingenuity and the power of careful, methodical engineering. They understood that reliability, not cutting-edge performance, would determine the mission's ultimate success. They built redundancy into every critical system, selected components for longevity rather than efficiency, and designed software that could adapt to circumstances they couldn't even imagine. The manufacturing techniques used to build Voyager 1 were largely manual, requiring skilled craftsmen who took pride in their workmanship. The spacecraft's aluminum frame was machined using conventional tools, with tolerances measured by hand and verified with mechanical gauges. The thousands of electrical connections were soldered individually by technicians who signed their work, taking personal responsibility for the quality of their craftsmanship. The companies that contributed components to Voyager 1 represented the pinnacle of American aerospace manufacturing in the 1970s. The spacecraft's structure was built by the Jet Propulsion Laboratory, but components came from suppliers across the country. The cameras were provided by the same company that made television cameras for the major networks. The computers were built using the most advanced microprocessors available at the time, which were primitive by today's standards but revolutionary for their era. The radioisotope thermoelectric generators that power Voyager 1 were manufactured using plutonium-238, produced specifically for space missions. This isotope is different from the plutonium used in nuclear weapons, but it required similar facilities and expertise to produce. The entire supply of plutonium-238 available in the United States in the 1970s was barely sufficient to power both Voyager spacecraft and a few other missions. Today, the production capacity for this crucial material has been largely lost, making missions like Voyager far more difficult to accomplish. The culture of excellence that permeated the Voyager program extended from the highest levels of NASA management to the individual technicians who assembled the spacecraft. Everyone involved understood that they were participating in something historically significant, a mission that would represent humanity's first serious attempt to explore the outer solar system. This sense of purpose and responsibility created an atmosphere of meticulous attention to detail that is rarely seen in modern engineering projects. The testing program for Voyager 1 was exhaustive, subjecting every component and subsystem to conditions far more severe than anything it would encounter during the actual mission. Components were vibrated until they failed, then redesigned to withstand even greater stresses. Electronics were subjected to radiation levels thousands of times higher than anything in space, then shielded to survive even these extreme conditions. The thermal vacuum testing that simulated the conditions of deep space required specialized facilities that could create near-perfect vacuums while subjecting components to temperature extremes. These tests revealed subtle problems that would never have been discovered in normal laboratory conditions. Components that worked perfectly at room temperature sometimes failed catastrophically when cooled to the temperatures of deep space. Materials that seemed stable in air sometimes outgassed volatile compounds in vacuum, contaminating sensitive surfaces. The launch of Voyager 1 represented the culmination of decades of technological development in rocket propulsion, spacecraft design, and mission planning. The Titan IIIe rocket that carried the spacecraft to space was one of the most powerful rockets available at the time, but even it was barely capable of delivering the massive spacecraft to the trajectory needed to reach Jupiter. Every kilogram of mass had to be justified, leading to endless trade-offs between scientific capability and engineering constraints. The trajectory calculations for Voyager 1's journey to Jupiter and Saturn required some of the most sophisticated mathematical modeling ever attempted. The spacecraft had to arrive at each planet at precisely the right time and location to achieve the desired gravitational assist, while also positioning itself optimally for scientific observations. These calculations had to account for the gravitational effects of all the major planets, the pressure of solar radiation, and even the tiny thrust from the spacecraft's radioisotope thermoelectric generators. The navigation team used mainframe computers that filled entire rooms and required specialized operators to program and maintain. The mathematical models they developed included thousands of variables and equations, representing the most accurate simulation of solar system dynamics ever created. Yet even these sophisticated models required constant refinement as new data became available from the spacecraft's actual trajectory. The precision required for Voyager 1's trajectory was extraordinary by any standard. The spacecraft had to arrive at Jupiter within a window of just a few hours, after traveling for nearly 2 years across 500 million miles of space. This level of accuracy is comparable to shooting an arrow from New York and hitting a target the size of a quarter in Los Angeles, while accounting for wind, gravity, and the rotation of the Earth. The encounter sequence at Jupiter required the spacecraft to execute a precisely choreographed series of observations while traveling past the planet at a speed of about 60,000 kilometers per hour. During the closest approach, Jupiter's gravity accelerated the spacecraft, adding energy that would carry it on to Saturn. The timing and geometry of this encounter were critical not only for the Saturn trajectory, but also for the scientific observations of Jupiter and its moons. The discovery of volcanic activity on Io during the Jupiter encounter came as a complete shock to the scientific team. The first hint came from navigation images that showed what appeared to be a crescent-shaped cloud extending from the moon's surface. Initially dismissed as an imaging artifact, this feature was later recognized as a volcanic plume ejecting material hundreds of kilometers above Io's surface. The implications of this discovery were staggering. Io is roughly the same size as Earth's moon, but it orbits much closer to Jupiter, where the giant planet's gravity creates tidal forces that heat the moon's interior. The volcanic activity on Io is so intense that the moon's entire surface is resurfaced by volcanic deposits every few thousand years, making it the youngest surface in the solar system. The sulfur compounds ejected by Io's volcanoes create a thin atmosphere around the moon and populate a donut-shaped torus of ionized gas around Jupiter's orbit. This discovery revealed that Jupiter's magnetic field traps charged particles from Io's volcanoes, creating radiation belts far more intense than anything around Earth. These radiation belts posed unexpected challenges for the Voyager spacecraft and had to be accounted for in the design of subsequent missions to Jupiter. Europa, the second of Jupiter's large moons, presented a completely different set of surprises. Its surface appeared to be composed entirely of water ice, with very few impact craters suggesting a geologically young surface. The ice was crisscrossed with long, linear fractures that resembled the pressure ridges seen in Arctic sea ice on Earth. These features suggested that Europa might have a liquid ocean beneath its icy crust, kept warm by tidal heating similar to that affecting Io. The possibility of a subsurface ocean on Europa immediately made it one of the most interesting targets for astrobiology, the search for life beyond Earth. On Earth, life exists in extreme environments, including the deep ocean floor, where no sunlight penetrates and organisms derive energy from chemical processes rather than photosynthesis. If Europa does have a liquid ocean, it might provide a similar environment where life could exist. Ganymede, the largest moon in the solar system, showed evidence of both ancient and more recent geological activity. Parts of its surface were heavily cratered, indicating great age, while other regions showed grooved terrain suggesting more recent tectonic activity. The contrast between these regions indicated that Ganymede had experienced a complex geological history, with periods of activity separated by long intervals of dormancy. Callisto, the outermost of Jupiter's large moons, appeared to be a relic from the early solar system, its surface saturated with impact craters accumulated over billions of years. The lack of any signs of geological activity suggested that Callisto had remained frozen throughout its history, preserving a record of the bombardment that shaped all the planets and moons during the solar system's violent youth. The ring system discovered around Jupiter was completely unexpected, since no ground-based telescope had ever detected any sign of Jovian rings. The rings are composed of tiny particles, probably debris from small moons or asteroids that have been pulverized by meteorite impacts. These particles are so small and sparse that they can only be seen when backlit by the sun, explaining why they had never been observed from Earth. The journey from Jupiter to Saturn took Voyager 1 through a region of space that had never been explored before. The spacecraft's instruments monitored the solar wind and cosmic ray environment, providing the first detailed measurements of conditions in the outer solar system. These data revealed that the solar system is much more dynamic than previously thought, with the solar wind varying significantly with distance from the sun and the solar activity cycle. The approach to Saturn provided the first close-up views of the planet's magnificent ring system, revealing a complexity that no Earth-based telescope could detect. What had appeared from Earth to be a few distinct rings separated by gaps proved to be thousands of individual ringlets, each with its own orbital characteristics and particle size distribution. The Cassini division, the most prominent gap in Saturn's rings, turned out to contain several faint rings of its own. The entire ring system resembled a cosmic phonograph record with intricate patterns that seemed to spiral inward and outward from the planet. These patterns are created by gravitational interactions with Saturn's many moons, which act as shepherds, sculpting and maintaining the ring structure through complex orbital resonances. The discovery that Titan, Saturn's largest moon, has a thick atmosphere was one of the most significant findings of the Saturn encounter. The atmosphere is composed primarily of nitrogen, like Earth's atmosphere, but it also contains methane and other organic compounds that give it an orange color. The atmospheric pressure at Titan's surface is about 1.5 times that of Earth, making it the only moon in the solar system with a substantial atmosphere. The organic chemistry taking place in Titan's atmosphere is thought to be similar to the processes that might have occurred on early Earth before life began. Complex organic molecules are constantly being created by the interaction of sunlight with methane and nitrogen in the upper atmosphere, then fall to the surface as a kind of organic snow. This process has been going on for billions of years, potentially creating a surface rich in the building blocks of life. The decision to target Titan for a close flyby meant that Voyager 1 could not continue on to visit Uranus and Neptune, a choice that mission planners debated for years. The scientific value of studying Titan's unique atmosphere was ultimately deemed more important than visiting the outer planets, a decision that was vindicated by the wealth of data obtained during the encounter. The gravitational assist from Saturn sent Voyager 1 on a trajectory that carried it above the plane of the solar system, beginning its journey toward interstellar space. This trajectory was carefully calculated to provide the fastest route out of the solar system while maximizing the scientific return from the interstellar mission. The spacecraft would spend the next 3 decades traveling through the outer regions of the heliosphere, studying the boundary between solar and interstellar space. The heliosphere, the bubble of space dominated by the solar wind, extends far beyond the orbit of Pluto. Its exact size and shape were unknown when Voyager began its journey, making the spacecraft a probe into truly unexplored territory. The heliosphere is not a static structure but responds dynamically to changes in solar activity, expanding and contracting as the solar wind varies in intensity. The termination shock, crossed by Voyager 1 in 2004, marked the boundary where the solar wind slows from supersonic to subsonic speeds as it encounters resistance from interstellar space. This boundary is not a fixed location, but moves back and forth as solar activity varies, sometimes by billions of kilometers. Voyager 1's passage through this region provided the first direct measurements of this dynamic boundary. The region beyond the termination shock, called the heliosheath, turned out to be far more turbulent and complex than scientists had expected. The solar wind, compressed and heated by its interaction with interstellar space, sometimes speeds up again, creating complex flow patterns that challenge our understanding of plasma physics. The magnetic field in this region shows unexpected variations, sometimes strengthening and sometimes nearly disappearing entirely. The boundary between the heliosphere and interstellar space, called the heliopause, proved to be remarkably sharp when Voyager 1 finally crossed it in 2012. Within a matter of days, the spacecraft detected dramatic changes in its environment. The density of charged particles increased by a factor of 40, while the magnetic field associated with the solar wind dropped to nearly zero. Yet the transition was not marked by any dramatic event that could be observed in real time. The environment of interstellar space revealed by Voyager 1 is unlike anywhere else the spacecraft had visited. The density of matter is extraordinarily low, with typically only 1 atom per cubic centimeter, yet this is still 40 times denser than the environment in the Helios heath. The temperature structure is complex, with electrons having energies corresponding to temperatures of thousands of degrees, while the overall kinetic temperature is only a few degrees above absolute zero. The magnetic field in interstellar space is stronger and more organized than scientists had predicted. This field appears to be aligned with the motion of the solar system through the galaxy, suggesting that it may be shaped by our solar system's interaction with the surrounding interstellar medium. The strength and orientation of this field have important implications for understanding how cosmic rays propagate through the galaxy. The cosmic ray environment in interstellar space is significantly different from what Voyager 1 encountered within the heliosphere. Cosmic rays are high-energy atomic nuclei that have been accelerated to nearly the speed of light by unknown mechanisms, probably involving the magnetic fields associated with exploding stars or other violent astronomical phenomena. Within the heliosphere, the solar wind partially shields us from these energetic particles, but in interstellar space, they are much more abundant. The discovery of the interstellar hum, first detected by Voyager 1 in 2017, represents one of the most subtle and sophisticated measurements ever made by the spacecraft. This faint oscillation in the interstellar plasma was so weak that it required years of data analysis to extract from the background noise. The hum provides direct information about the density and distribution of matter in the local interstellar medium. The plasma wave instrument that detected the interstellar hum was designed in the 1960s using analog electronics and magnetic tape recording systems. The fact that this decades-old instrument could make such a precise measurement demonstrates the value of careful engineering and conservative design. Modern digital instruments might be more sophisticated, but they would be hard-pressed to improve on the reliability and longevity of the Voyager systems. The data analysis techniques used to extract the interstellar hum from the background noise represent a triumph of modern signal processing. Scientists used sophisticated algorithms to filter out interference from the spacecraft's own systems and from solar activity, leaving only the faint signature of oscillations in the interstellar plasma. This analysis required years of work by teams of specialists who understood both the physics of plasma waves and the characteristics of the Voyager instruments. The continuing operation of Voyager 1 has required the mission team to develop new techniques for managing spacecraft resources and extending operational life. As power has declined and components have aged, engineers have had to find creative solutions to problems that were never anticipated during the original design phase. These solutions often involve reprogramming the spacecraft's computers or using systems in ways that were never intended by the original designers. The software that runs Voyager 1's computers has been modified hundreds of times since launch, with new code uploaded to adapt to changing conditions or work around failed components. This software maintenance is complicated by the fact that the programming languages and computer architectures used by Voyager are no longer in common use. The engineers who maintain these systems must understand computing technologies that are essentially obsolete everywhere except on these two spacecraft. The institutional memory required to operate Voyager 1 represents one of NASA's most valuable assets. Many of the engineers who designed and built the spacecraft have retired or passed away, but their knowledge has been carefully preserved and passed on to younger engineers. This continuity of expertise is crucial for maintaining operations as the spacecraft encounters new challenges in interstellar space. The daily routine of operating Voyager 1 begins with downloading data from the previous day's activities and analyzing it for any signs of problems or unexpected behavior. Engineers must then plan the next day's activities, balancing scientific objectives against power constraints and communication schedules. Every command sent to the spacecraft must be carefully checked and double-checked, since the long communication delay makes it impossible to correct mistakes quickly. The Deep Space Network facilities that communicate with Voyager 1 represent some of the most sophisticated radio astronomy installations in the world. The 70-meter antennas used for Voyager communications are so sensitive that they can detect radio signals from galaxies billions of light years away. Yet even these massive antennas must strain to hear the faint whisper of Voyager 1's transmitter across the vast distance of interstellar space. The signal processing techniques used to extract data from Voyager 1's transmissions have evolved dramatically since the mission began. Originally, the spacecraft's digital data was recorded on magnetic tape and processed using techniques developed for telephone communications. Today, sophisticated computer algorithms can extract useful information even when the signal is almost completely overwhelmed by noise. The error correction codes used in Voyager 1's data transmissions were state-of-the-art in the 1970s but seem primitive by modern standards. Yet these codes continue to work reliably, allowing ground controllers to detect and correct errors in the received data. When combined with modern signal processing techniques, these old-fashioned error correction methods can recover data even under conditions that would make communication impossible with less robust systems. The scientific value of the data being returned by Voyager 1 from interstellar space continues to exceed expectations. Every measurement provides new insights into an environment that cannot be studied in any other way. The spacecraft is sampling a region of space that represents the typical conditions between stars throughout our galaxy, providing a kind of ground truth for astronomical observations made from Earth. The magnetic field measurements made by Voyager 1 in interstellar space are particularly valuable because they provide direct information about the large-scale structure of our galaxy's magnetic field. This field plays a crucial role in the evolution of stars and the propagation of cosmic rays, but it can only be studied indirectly from Earth. Voyager 1's measurements provide the first direct sampling of this fundamental component of galactic structure. The particle measurements made by Voyager 1 reveal the composition and energy distribution of matter in the local interstellar medium. These measurements show that interstellar space contains a complex mixture of different types of particles, from low-energy ions to high-energy cosmic rays. Understanding this particle environment is crucial for planning future interstellar missions and for understanding the conditions that spacecraft will encounter in the space between stars. The plasma wave measurements made by Voyager 1 provide information about the temperature and density of the interstellar medium that cannot be obtained in any other way. These measurements reveal that interstellar space is not empty and uniform, but contains waves and turbulence generated by the complex interactions between stellar winds and the remnants of ancient supernovae. The longevity of Voyager 1's journey puts its achievements in a completely different temporal context from most human endeavors. The spacecraft has now been operating longer than many of the engineers who built it have been alive. It has outlasted the Soviet Union, the Berlin Wall, and countless technological revolutions. It has become a kind of time machine, carrying 1970s technology into an era of smartphones and social media. The perspective provided by Voyager 1's long journey offers a unique view of human technological progress. When the spacecraft was launched, the personal computer revolution was just beginning. The internet existed only as a research project. Cell phones were bulky devices used by a few business executives. Most people got their news from newspapers and television. The idea that ordinary people would one day carry devices more powerful than the computers that guided Voyager to Jupiter seemed like science fiction. Yet the fundamental principles that made Voyager 1 successful remain as relevant today as they were in 1977. Careful engineering, attention to detail, conservative design, and thorough testing are still the hallmarks of successful spacecraft. The mission demonstrates that reliability and longevity are often more valuable than cutting-edge performance, a lesson that applies to many areas of technology and engineering. The cultural impact of Voyager 1 has evolved over the decades as our understanding of the mission's significance has deepened. Initially celebrated as a triumph of exploration and discovery, the mission has come to symbolize humanity's ability to transcend the limitations of our home planet. The pale blue dot photograph has become an icon of environmental consciousness, reminding us of Earth's fragility and uniqueness in the cosmic perspective. The golden record has taken on a life of its own in popular culture, inspiring musicians, artists, and writers around the world. The record's contents have been analyzed and reinterpreted countless times, with each generation finding new meanings in this message from Earth to the cosmos. The record represents an idealized version of humanity, emphasizing our achievements in science, art, and culture, while omitting the darker aspects of human nature. The music on the golden record represents one of the most eclectic collections ever assembled, ranging from Bach's Brandenburg Concerto No. 2 to Chuck Berry's Johnny B. Goode, from traditional folk songs to modern classical compositions. The selection process was both collaborative and contentious, with committee members struggling to represent the full diversity of human musical expression within the constraints of a single phonograph record. The spoken greetings on the golden record were recorded in 55 languages, representing a remarkable diversity of human linguistic expression. Each greeting was unique, reflecting the cultural perspective of its speaker while attempting to convey a message of peace and goodwill. The greetings range from simple salutations to more complex statements about human nature and our place in the universe. The sounds of Earth included on the golden record were chosen to represent the acoustic environment of our planet. Natural sounds like wind, rain, and ocean waves capture the physical environment that shaped human evolution. Biological sounds like bird songs, whale calls, and human laughter represent the rich tapestry of life that makes Earth unique. Human-made sounds like footsteps, heartbeats, and the sound of a kiss represent the more intimate aspects of human experience. The images on the golden record include both scientific diagrams and artistic photographs intended to convey the beauty and complexity of life on Earth. The scientific images include mathematical definitions, anatomical diagrams, and illustrations of DNA structure, providing a kind of primer on human knowledge and biology. The artistic images show landscapes, animals, and people from around the world, representing the diversity of Earth's environments and cultures. The technical specifications for playing the golden record assume that any civilization advanced enough to intercept Voyager would also be capable of understanding basic physics and mathematics. The instructions use pictographs and mathematical symbols to explain how to extract audio and visual information from the record using the wavelength of hydrogen as a universal unit of measurement. The materials and construction of the golden record were chosen for maximum longevity. The record itself is made of gold-plated copper, selected for its resistance to corrosion and its ability to maintain surface quality over cosmic timescales. The protective cover is made of aluminum and includes diagrams explaining how to play the record. According to its designers, the golden record should remain playable for over 1 billion years. The philosophical implications of the golden record continue to generate debate among scholars and thinkers around the world. The record represents humanity's first serious attempt to communicate with a non-human intelligence, forcing us to think about what makes us uniquely human and what aspects of our civilization we consider most important. The selection process required its creators to step outside their own cultural assumptions and try to see humanity from an external perspective. As Voyager 1 continues its journey through interstellar space, it is gradually moving away from the Sun at a speed of about 17 kilometers per second. This may seem fast by human standards, but it is actually quite slow compared to the vast distances between stars. At its current speed, Voyager 1 will not come close to another star for tens of thousands of years. The trajectory of Voyager 1 through the galaxy will carry it through regions of space that have never been visited by any human artifact. Over the millions of years of its journey, the spacecraft will encounter different types of interstellar environments, from the relatively empty space between spiral arms to the denser regions near star-forming nebulae. Each environment will subject the spacecraft to different conditions of radiation, magnetic fields, and particle bombardment. The probability that Voyager 1 will ever be found by an extraterrestrial civilization is extraordinarily small. Frank Drake, one of the scientists involved in designing the Golden Record, estimated the probability at less than 1 in a trillion. Yet even this tiny probability represents a meaningful chance that humanity's message will someday be received and understood by another intelligent species. The longevity of Voyager 1's journey through the galaxy puts its mission in the same temporal context as geological and astronomical processes. The spacecraft will witness the evolution of stars, the formation of new planetary systems, and cosmic events that we can only imagine. It will outlast not only our current civilization, but potentially our entire species, carrying its message into a future we cannot comprehend. The peaceful nature of Voyager 1's message stands in stark contrast to many of humanity's earthly endeavors. The Golden Record contains no images of war, violence, or human suffering, presenting instead an idealized version of human civilization. This choice was deliberate, reflecting Carl Sagan's belief that the record should represent humanity at its best, not its worst. The scientific instruments aboard Voyager 1 continue to reveal new aspects of the interstellar environment as the spacecraft travels deeper into interstellar space. Recent measurements suggest that the spacecraft may be entering a different region of the interstellar medium with slightly different properties than the region it first encountered after leaving the heliosphere. The temperature measurements in interstellar space reveal a complex environment where different components of the medium exist at vastly different temperatures. The overall kinetic temperature is only a few degrees above absolute zero, yet individual electrons have energies corresponding to temperatures of thousands of degrees. This temperature structure provides clues about the energy sources that heat the interstellar medium. The density measurements made by Voyager 1 show that interstellar space is remarkably uniform, with only subtle variations that provide evidence for waves and turbulence in the interstellar plasma. These variations are probably generated by stellar winds from nearby stars and the expanding shock waves from ancient supernovae, creating a complex web of interactions throughout the galaxy. The cosmic ray measurements made by Voyager 1 in interstellar space are providing new insights into the origin and acceleration of these mysterious high-energy particles. The spacecraft's unique position outside the heliosphere allows it to measure cosmic rays that have not been affected by the solar wind, providing a clearer picture of the galactic cosmic ray environment. The magnetic field measurements continue to reveal unexpected structure in the interstellar magnetic field. The field appears to be more organized than scientists had expected, suggesting that it may be shaped by large-scale galactic processes such as the rotation of the galaxy or the collective effect of stellar winds from many stars. The ongoing discoveries being made by Voyager 1 in interstellar space demonstrate that even after nearly 5 decades of operation, the mission continues to push the boundaries of human knowledge. Each new measurement provides insights that cannot be obtained in any other way, making every day of continued operation scientifically valuable. The engineering challenges of maintaining Voyager 1 in working condition continue to test the ingenuity of the mission team. As components age and power levels decline, engineers must find creative solutions to problems that were never anticipated during the original design phase. These solutions often involve using systems in ways that were never intended by the original designers. The power management challenges become more critical with each passing year as the radioisotope thermoelectric generators produce less electricity. Mission managers must make increasingly difficult decisions about which instruments to keep operating and which to shut down, balancing scientific priorities against power constraints. The thruster system challenges have required innovative solutions as fuel lines become clogged with decomposition products from the hydrazine fuel. Engineers have developed techniques for switching between different sets of thrusters and even reviving thrusters that had been dormant for decades, extending the spacecraft's ability to maintain proper orientation. The communication challenges grow more severe as Voyager 1 moves farther from Earth and its transmitter power declines. The Deep Space Network must use increasingly sophisticated techniques to extract useful data from signals that are barely distinguishable from background noise. The data processing challenges require specialized expertise in obsolete computer systems and programming languages. The engineers who maintain Voyager 1's software must understand technologies that are no longer used anywhere else, making their knowledge irreplaceable and requiring careful preservation for future generations. The scientific data analysis challenges are complicated by the fact that Voyager 1 is exploring completely unknown territory. Scientists must develop new theoretical models and analysis techniques to understand the data being returned from interstellar space, often pushing the boundaries of our understanding of plasma physics and space science. The institutional challenges of maintaining a mission for nearly 5 decades have required NASA to develop new approaches to project management and knowledge preservation. The mission has outlasted many of the managers and engineers who originally planned and designed it, requiring careful documentation and knowledge transfer to ensure continuity. The funding challenges of supporting a decades-long mission have required creative approaches to budget management and resource allocation. The Voyager program has survived numerous budget cuts and organizational changes, demonstrating the enduring value of well-planned and well-executed space missions. The international cooperation that has characterized the Voyager program continues to benefit scientific understanding around the world. Data from the spacecraft are shared freely with researchers from many countries, fostering collaboration and advancing knowledge across national boundaries. The educational impact of Voyager 1 continues to inspire new generations of students and researchers. The mission provides compelling examples of how theoretical knowledge can be applied to solve practical problems, demonstrating the value of basic research and scientific education. The technological legacy of Voyager 1 continues to influence spacecraft design and mission planning decades after its launch. The conservative engineering approach that has made Voyager so successful continues to guide the development of new deep space missions, and so Voyager 1 continues its eternal journey, a small speck of human engineering moving silently through the vast darkness between stars. Its instruments still function, though not as perfectly as they once did. Its transmitter still sends data across the enormous gulf of space, though the signals grow weaker with each passing year. Its golden record still carries its message of peace and hope, waiting patiently for a recipient that may never come. In the cosmic perspective, Voyager 1's journey has barely begun. The spacecraft will travel through interstellar space for millions of years, long after our sun has died and our Earth has been reduced to cosmic dust. It will witness the birth and death of countless stars, the collision of galaxies, and cosmic events beyond our imagination. In a very real sense, Voyager 1 has achieved a form of immortality, carrying a piece of human consciousness into the far future. The steady rhythm of its electronics, the patient sweep of its instruments, the gentle pulse of its transmitter, all continue in the timeless dance of exploration and discovery. In that rhythm, there is something deeply peaceful, something that speaks to the eternal human desire to reach beyond our limitations and touch the infinite mystery that surrounds us. The individuals who dedicated their careers to Voyager 1 represent a remarkable generation of engineers and scientists who possessed both technical brilliance and an almost romantic vision of exploration. Many of them had grown up during the early days of the space age, inspired by the first satellites and moon landings to pursue careers in aerospace engineering and planetary science. They brought to the Voyager program not just technical expertise, but a sense of adventure and wonder that permeated every aspect of the mission. Charles Colhayes, the mission design manager for Voyager, spent years calculating the precise trajectories that would carry both spacecraft through their encounters with the outer planets. His work required an intuitive understanding of celestial mechanics combined with meticulous attention to detail. Every calculation had to be checked and rechecked, since small errors could result in mission failure. Kohlhase and his team worked with slide rules and early computers, creating navigation plans that remain marvels of precision and foresight. Bradford Smith, the leader of the imaging team, oversaw the selection and operation of the cameras that captured Voyager's most famous photographs. He had to balance the scientific requirements for systematic mapping and measurements against the desire to capture images that would inspire and educate the public. The iconic images of Jupiter's swirling clouds and Saturn's intricate rings reflect both scientific rigor and artistic sensibility. Edward Stone, the project scientist for Voyager, served as the scientific conscience of the mission, ensuring that every decision was made with the goal of maximizing scientific return. He had to mediate between competing scientific interests while maintaining focus on the mission's primary objectives. His leadership helped create a collaborative atmosphere where scientists from different disciplines worked together toward common goals. Linda Spilker, who began her career working on Voyager data analysis and eventually became the project scientist, represents the continuity of expertise that has kept the mission operating for nearly 5 decades. She has witnessed the spacecraft's evolution from planetary explorer to interstellar probe, adapting her research focus as the mission has evolved. Her work demonstrates the value of long-term scientific dedication and the rewards of patience in scientific exploration. The technicians and engineers who built Voyager 1 brought to their work a level of craftsmanship that is rarely seen in modern manufacturing. Every solder joint was inspected under magnification. Every wire was routed with care to avoid electromagnetic interference. Every mechanical connection was tested to ensure it would remain secure under the stresses of launch and the thermal cycling of space. These workers took personal pride in their contributions to the mission, understanding that the quality of their work would determine the spacecraft's ultimate success. The machinists who fabricated Voyager 1's aluminum frame worked with tolerances measured in thousandths of an inch, using techniques that required years of training and experience to master. They understood that their work would have to withstand not just the violent acceleration of launch, but decades of thermal expansion and contraction as the spacecraft moved between the heat of sunlight and the cold of shadow. The electronics technicians who assembled Voyager 1's computers and instruments worked with components that were manufactured to the highest standards available in the 1970s. They understood that every connection had to be perfect, since there would be no opportunity for repairs once the spacecraft left Earth. Their work required not just technical skill, but an almost obsessive attention to detail. The quality assurance engineers who tested every component of Voyager 1 developed procedures that pushed the boundaries of what was considered necessary for spacecraft construction. They subjected components to vibration levels far exceeding anything the spacecraft would encounter during launch. They exposed electronics to radiation doses thousands of times higher than anything in the space environment. They tested materials under temperature extremes that went far beyond the mission requirements. The culture of excellence that characterized the Voyager program extended to every aspect of the mission, from the highest levels of management to the individual workers who cleaned the spacecraft before launch. Everyone involved understood that they were participating in something historically significant, and this awareness created a sense of responsibility that motivated extraordinary effort and attention to detail. The launch preparation for Voyager 1 required months of careful planning and coordination between dozens of organizations. The spacecraft had to be transported from the Jet Propulsion Laboratory in California to Kennedy Space Center in Florida, a journey that required special handling procedures to protect the delicate instruments and electronics. Every aspect of the transportation was planned in detail, with backup procedures for every conceivable problem. The integration of Voyager 1 with its launch vehicle required precise alignment and careful attention to weight distribution. The spacecraft's center of mass had to be positioned exactly to ensure stable flight during ascent. The electrical connections between the spacecraft and the rocket had to be designed to separate cleanly at the moment of spacecraft separation. These seemingly simple tasks actually required weeks of careful work by teams of specialists. The final countdown for Voyager 1's launch was delayed several times due to technical problems and weather conditions. Each delay required careful analysis to ensure that the spacecraft would still arrive at Jupiter at the optimal time for the gravitational assist maneuver. The launch window was constrained not just by orbital mechanics, but by the positions of Jupiter and Saturn, which determined the geometry of the entire mission. The moment of launch itself represented the culmination of a decade of planning and preparation. As the Titan rocket lifted off from Cape Canaveral, it carried with it the hopes and dreams of thousands of people who had worked to make the mission possible. The successful launch was just the beginning of a journey that would test every aspect of the spacecraft's design and the skills of the mission team. The early days of the Voyager 1 mission were filled with the routine tasks of checking out the spacecraft's systems and calibrating its instruments. Engineers had to verify that all systems had survived the violent acceleration of launch and were functioning properly in the space environment. This checkout process revealed several minor problems that were quickly resolved, demonstrating the value of thorough ground testing and careful system design. The cruise phase of the mission, as Voyager 1 traveled from Earth to Jupiter, provided opportunities to refine operational procedures and test new techniques for spacecraft navigation and control. The mission team used this time to develop the detailed procedures that would be needed during the planetary encounters, when split-second timing would be critical for success. The trajectory corrections needed to keep Voyager 1 on course for Jupiter were calculated with extraordinary precision. Each correction required firing the spacecraft's thrusters for carefully calculated periods of time, changing the spacecraft's velocity by just a few meters per second. These small adjustments, made over the course of nearly 2 years, ensured that the spacecraft would arrive at Jupiter at exactly the right time and place. The navigation team tracked Voyager 1's progress using radio signals transmitted from the spacecraft to antennas on Earth. By measuring tiny Doppler shifts in these signals, navigators could determine the spacecraft's position and velocity with remarkable accuracy. This technique, called radiometric navigation, requires extraordinary precision in both the spacecraft's transmitter and the ground-based receiving equipment. The approach to Jupiter began months before the actual encounter, as Voyager 1's instruments started detecting changes in the space environment around the giant planet. The spacecraft's magnetometer began registering the influence of Jupiter's massive magnetic field, while still millions of kilometers away. The particle detectors started measuring energetic electrons and ions trapped in Jupiter's radiation belts. These early measurements provided the first hints of the discoveries to come. The imaging team began taking regular pictures of Jupiter while still far from the planet, creating time-lapse movies that showed the complex dynamics of the planet's atmosphere. These images revealed that Jupiter's atmosphere is far more turbulent and dynamic than had been suspected, with storm systems that develop and dissipate over periods of days or weeks. The discovery of lightning on Jupiter came from measurements made by Voyager 1's radio astronomy instrument, which detected the characteristic radio bursts produced by electrical discharges in the planet's atmosphere. This discovery was significant because it suggested that Jupiter's atmospheric chemistry might be more complex than previously thought, with electrical processes playing a role in the formation of complex organic molecules. The measurements of Jupiter's magnetic field revealed that it is far stronger and more complex than Earth's magnetic field. The field appears to be generated by electrical currents in Jupiter's metallic hydrogen core, a state of matter that exists only under the extreme pressures found deep inside the giant planet. This discovery provided new insights into the internal structure and composition of Jupiter. The radiation environment around Jupiter proved to be far more intense than mission planners had expected. Voyager 1's electronics were subjected to radiation levels thousands of times higher than anything in Earth orbit, causing some instruments to malfunction temporarily and requiring careful management of the spacecraft's exposure time. These measurements provided crucial data for planning subsequent missions to Jupiter. The discovery of a ring system around Jupiter came as a complete surprise to the scientific team. The rings are composed of tiny particles, probably debris from small moons or asteroids that have been pulverized by micrometeorite impacts. The rings are so faint that they can only be seen when backlit by the sun, explaining why they had never been detected by Earth-based telescopes. The detailed study of Jupiter's 4 large moons revealed that each is a unique world with its own geological history and characteristics. Io's volcanic activity was the most dramatic discovery, but each moon provided new insights into the processes that shape planetary bodies throughout the solar system. The gravitational assist maneuver at Jupiter was executed perfectly, accelerating Voyager 1 towards Saturn while providing optimal conditions for scientific observations. The precise timing of this maneuver was critical not just for reaching Saturn, but for determining the entire trajectory of the spacecraft's subsequent journey into interstellar space. The journey from Jupiter to Saturn took Voyager 1 through a region of space that had never been explored before. The spacecraft's instruments monitored the solar wind and magnetic field environment, providing new insights into the structure of the solar system's magnetic field and the interaction between the solar wind and interplanetary space. The approach to Saturn began with the gradual resolution of the planet's ring system, revealing complexity that far exceeded anything that had been observed from Earth. The rings, which had appeared from Earth to be a few simple bands, were revealed to be thousands of individual ringlets with intricate structure and dynamics. The discovery of spokes in Saturn's rings was one of the most unexpected findings of the Saturn encounter. These dark, radial features appear and disappear over periods of hours, apparently related to electromagnetic effects in the ring system. The spokes demonstrate that Saturn's rings are not simply collections of orbiting particles, but dynamic systems influenced by electromagnetic forces. The complex orbital resonances that shape Saturn's ring system became apparent from Voyager 1's detailed observations. Small moons embedded within the rings act as shepherds, using gravitational forces to maintain the sharp edges of ring divisions and create the intricate structure observed in high-resolution images. The encounter with Titan provided the first close-up look at this enigmatic moon, revealing a thick atmosphere that completely obscures the surface. The atmosphere is composed primarily of nitrogen, like Earth's atmosphere, but also contains methane and complex organic compounds that give it a distinctive orange color. The atmospheric pressure on Titan's surface is about 1.5 times that of Earth, making it the only moon in the solar system with a substantial atmosphere. The temperature is extremely cold, about minus 180 degrees Celsius, but the presence of liquid methane and ethane creates a hydrological cycle similar to the water cycle on Earth, with clouds, precipitation, and possibly rivers and lakes of liquid hydrocarbons. The organic chemistry taking place in Titan's atmosphere represents a natural laboratory for studying the kinds of processes that might have occurred on early Earth before life began. Complex organic molecules are constantly being created by photochemical reactions in the upper atmosphere, then settling to the surface as a kind of organic snow. The decision to target Titan for a close flyby meant that Voyager 1 could not continue to Uranus and Neptune, leaving those planets to be explored by Voyager 2. This choice reflected the scientific community's recognition that Titan might be one of the most interesting and potentially habitable worlds in the solar system. The gravitational assist from Saturn sent Voyager 1 on a trajectory that carried it out of the plane of the solar system, beginning its journey toward interstellar space. For 35 years, the spacecraft traveled through the outer regions of the heliosphere, watching the solar wind gradually decelerate and distort as it encountered resistance from interstellar space. The crossing of the termination shock in 2004 marked Voyager 1's entry into the heliosheath, a turbulent boundary region that proved far more complex than scientists had predicted. The solar wind sometimes accelerated again, the magnetic field showed unexpected variations, and the entire environment challenged existing theoretical models. The final crossing into interstellar space in 2012 was remarkably sharp. Within days, the density of charged particles increased by a factor of 40, while the solar wind's magnetic field dropped to nearly zero. Suddenly, Voyager 1 found itself sampling true interstellar space, an environment quite different from scientific expectations. Rather than being empty and uniform, interstellar space contains a complex mixture of gas, dust, magnetic fields, and high-energy particles. The interstellar magnetic field proved stronger and more organized than predicted, apparently aligned with our solar system's motion through the galaxy. The temperature structure is remarkably complex, with overall kinetic temperatures near absolute zero, yet individual electrons carrying energies equivalent to tens of thousands of degrees. Most remarkably, Voyager 1 discovered the interstellar hum, a faint oscillation in the interstellar plasma so weak that it required years of sophisticated analysis to extract from background noise. This subtle measurement provides direct information about the density and structure of the space between stars. Maintaining Voyager 1's operation in this alien environment requires increasingly creative solutions. Engineers have successfully switched between different thruster sets, revived systems dormant for decades, and continuously modified decades-old software to work around failing components. The spacecraft's declining power forces difficult daily decisions about which instruments to keep operating, while the Deep Space Network has been repeatedly upgraded to maintain communication across the ever-growing distance. The mission's legacy extends far beyond its scientific discoveries. The Golden Record has become perhaps the most analyzed cultural artifact ever created, raising profound questions about how we represent humanity to potential alien intelligences. The conservative engineering approach that made Voyager so successful continues to influence spacecraft design, while the mission has inspired generations of students to pursue careers in science and engineering. The longevity of Voyager 1's journey has given it temporal significance, extending far beyond typical human timescales. The spacecraft has operated longer than many of its builders lived, becoming a technological time capsule carrying 1970s engineering into our modern era. It demonstrates that careful planning, conservative design, and dedication to excellence can produce results that far exceed original expectations. As Voyager 1 continues its journey into the unknown, it carries with it the collective hopes and dreams of our species. In a universe that often seems indifferent to human existence, this small machine represents our refusal to accept limitations, our determination to explore and understand, and our faith that knowledge can triumph over ignorance. The spacecraft moves through the darkness between stars at 17 kilometers per second, a speed that seems incredible by earthly standards, yet almost motionless compared to interstellar distances. Its journey will continue long after our civilization has been forgotten, long after our planet has been consumed by an expanding sun. In that cosmic perspective, there is something deeply moving about Voyager 1's patient persistence. Its instruments continue sampling an environment no human will ever visit directly. Its transmitter whispers data across an expanding gulf of space and time. Its golden record carries our message into an uncertain future. The story of Voyager 1 is ultimately about the power of human curiosity and the courage to seek answers to fundamental questions about our place in the universe. In the silence of deep space, where no sound can travel, Voyager 1 continues to speak for all of us, its steady electronic heartbeat marking time in an environment where time itself seems meaningless. As you drift towards sleep, imagine this small ambassador of humanity moving through the cosmic night, its mission continuing, its message traveling toward destinations we cannot imagine. In its steady journey through the dark, there is profound peace, a reminder that exploration and discovery can be gentle acts of hope and wonder, reaching across impossible distances to touch the infinite mystery that surrounds us all.